Vigyan Bharti with Avilas Sarkar. We are just reaching the last problem of fluid statistics, that is problem number 50. Then after we'll move on to the the subjects which are the, you can say, the second part of the fluid mechanics, that is fluid dynamics. Okay, so let's start with the last problem, the problem number 50 of fluid statistics. It says a concrete sphere, a concrete sphere of radius capital R has a cavity of radius smaller which is packed with which is packed with sawdust. Okay, the specific gravities of concrete and sawdust are respectively 2.4 and 0.3 for 3.3. This is for this sphere to float with its entire volume submerged underwater ratio of mass of concrete to sawdust is underwater. Find the ratio. Okay, so what does it say? That the concrete sphere of radius R, if I draw the concrete sphere, it is a spherical one having a hollow part inside. Okay, the radius of the concrete sphere is of capital R, that hollow is of R. So this void is filled with sawdust. This is a solid concrete. Now what is happening? Which is packed with the sawdust, the specific gravity is given. Okay, fine. For this sphere to float with the entire volume submerged under the water. So let's say if I show it in a very small scale, this is the water, it is just floating, submerging its complete volume. Okay, so this is the a solid ball, this is the solid concrete and this is being filled with sawdust. This is so if it is in submerged under the water and it is in steady state condition, it is in equilibrium, it is in means floating condition, submerged and floating condition. That means my equation will be the weight of the concrete plus sawdust will be the buoyancy. Okay, there is no other force is acting, so buoyancy upward and that is balancing each other. What is the weight of this? Weight of the concrete plus weight of the sawdust differently is equal to buoyancy is the volume of water into rho of water into G. The volume of water dispersed by this, so dispersed by this that is the complete volume. Weight of the concrete, that means it is a sphere 4 by 3 pi r. The volume will be this one will be the, let me draw it step by step, means put it step by step. Volume of the concrete, rho of concrete into G, volume of the sawdust, rho of sawdust into G, and that of volume of water dispersed, rho of water, then density of water, and G. So G is not used, so ultimately the equation will become volume of concrete, rho of concrete, plus volume of sawdust, rho of sawdust is equal to volume of water, rho of water. Fine. Now volume of concrete 4 by 3 as per the spherical volume, that is equal to 4 by 3 pi r cube, where this is the r. Now for this case there is a way hollow part, so that will not be considered as a volume. The ultimate volume will be this part, will be the common part, and for the whole thing it will be the r cube. The radius of this, the total is r, and this hollow part has to be deducted, so that will be the minus 4 by 3 pi r cube, that has to be deducted, and the rho of the concrete plus for this sawdust it will be the volume that is filled with sawdust, that will be the lower diameter r cube, this is the volume, into the density of the sawdust. And for this case what I will take, the external, so that means the this one, the volume in this case will be 4 by 3 pi r cube, the external surface, external volume, so that equal amount of water will be dispersed into rho w. Okay. Now I will rubbing this part because this is not very necessary right now. So 4 by 3, this all can be cancelled out because everything there. So what is remaining? R cube minus R cube into this one you can put the value, the concrete 2.4. Okay. As we can see, you can take all in same unit, so unit will be cancelled out, whether I take it in SI or CGS, that doesn't mean. So because the unit will be cancelled, so I am just putting the values only, plus r cube into this is 0.3 sawdust, and this is equal to r cube into 1 I am taking. Okay. So this are equal, so one doesn't have any different meaning. So what are the remaining now? R and R, if I take one side, so this is r cube, this is r cube, so this minus this will be 1.4 r cube will be there, and this part if I take 2.4 minus 0.3 2.1, so this will come this side 2.1 r cube. So if I cancel it with 7, this will be 0.7273. So your equation will become r cube means 2r cube is equal to 3r cube, small r cube. So this is, now you have to compare the mass of the mass of the concrete. So mass of the concrete is the volume into their mass of concrete by mass of sawdust you have to calculate. So volume into density. The volume of the concrete is 4 by 3 pi r cube minus r cube into the density, that is equal to concrete 2.4, and this is equal to sawdust pi r cube into 0.3. Okay, so this will cancel 8, this will cancel, so this is become r by small r by capital R cube minus 1 whole into 8. So this is equal to r by r is equal to capital R by small r whole cube, that is equal to 3 by 2. So 3 by 2 minus 1, so half into 8, so that is equal to 4. So the ratio is 4:1. Your answer will be 4:1. Concrete is to sawdust. This is the recurrent concrete to sawdust. Okay, fine. So this is the end of the problem solving session of fluid statistics. Now we have covered fluid statistics theory as well as 50 number problem we solved. Now the next part is fluid dynamics. So which is the second part of fluid mechanics. So this is the second part which comes under fluid mechanics is fluid dynamics. So what is that? So what we mean by dynamic is that earlier cases we have assumed the case when fluid is not flowing, so there is no flow. So in this case we first consider will be fluid is flowing. So when fluid will flow, the consideration will change from statics to dynamics. So wherever there is a fluid which is flowing, we will consider that subject to be considered under fluid dynamics. Fine. So now what else we can think of? So if I can assume a conduit, okay, which is of circular shape, and some fluid is flowing through it. Yes, a fluid is flowing through it, taking the shape of the liquid. Okay, so this comes under the study of fluid dynamics. Now, to study the fluid dynamics, the first subject that is coming is the kind of flow. This is comes under kind of flow. There is a flow we have accepted. Now, what are the kind of flow that may arise during this study? Though out of this, first one is steady, or that can be named as streamline, or that can be named as laminar, and these are all of a kind of dynamic comes first type of flow, because flow is there, so subject is dynamic. So the type that comes, the kind of flow is steady, streamline or laminar. The second of its kind is turbulence. Okay. So these are the two extreme kind of flow. One is steady, streamline or laminar, all are same. Second kind is turbulence. In between there is another flow that is called unsteady flow. So let us understand theoretically or physically what are those, and that has to be understood with a try to bring some condition properties of the this kind of flow. First, physically, what do you understand by steady flow or turbulence or the unsteady flow? Now, the simplest one, if I can say that there is a tank, okay, and there is a pipe attached to it, okay, a simple uniform pipe is attached to it, and this tank is filled with water, because whatever we'll discuss on some consideration, because we are considering the fluid that we have also considered in case of statistics. The fluid is, the first assumption is incompressible. Okay, so first assumption is incompressible, so there is no change of density in the fluid where we'll study even fluid dynamics. Okay, there is not being affected. That means fluid properties, whether it is velocity or pressure or something, won't change. This is incompressible. Okay, so that we are talking about. Now let's say this is one arrangement. There is a tank and this is so this is filled with water. Now suddenly you open, there may be a lid and open. So the fluid flowing through this will flow very gently, uniformly. If it is allowed to flow on the surface, it will flow very gently, a very smooth way. Means even though if there is no bend, it will form a bend and it will fall down uniformly on it. Okay. So if this tank is not very big, it is not very big, and the pressure difference to this point is not much, it is not considered to be very much pressure. So if you can see, you can observe this liquid, or at least we can consider the water. If this water will fall uniformly, there is no path which will find that cross section is almost similar. It is same way this is falling. The cross section along the line is very similar and falling very smoothly, and the height is not considered to be very high. Means there is no much of the elevation in this water being stored. Okay, so this kind of flow comes under the steady flow, streamline flow. That means there is no much variance in the flow, that is smoothly flowing. Okay, suddenly somebody tries to block this, means with something, maybe with some obstacle. They try to restrict the path. So what will happen? This flow will not able to flow through this path, rather it will try to avoid this resistance and try to move the free path, whatever is there, will through that path, and it will fall. Okay, so so this kind of flow after this restriction will not be a very smooth flow. That is a very haphazard flow. That is very restricted and absurd flow you will get. Means all the whatever water you are flowing in everywhere around the restriction, it will flow without any particular direction. It may flow that side or this side, anywhere it can flow, and this may be due to the shape of the restriction. It may flow in any direction. There is no fixed direction, or almost it will be haphazard, means totally disturbed flow. So this kind of flow is comes under the turbulence flow. So steady flow can convert into the turbulence flow due to the restriction. Okay, now where this unsteady flow will come? Where this unsteady flow will come? So the unsteady flow is in between the steady flow and the turbulence flow, where what we do, let's say this pipeline is being extended a bit. Okay, extended a bit, and this water again without restriction it will flow and flow in a uniform manner. Okay, fine. But let's say there is a valve is also there in this path. There is a valve or restriction, you can say. Okay, so now initially this valve is not in picture, so it is trying to flow as smoothly as earlier without valve. Now suddenly the valve is restricting some of the path, blocking some of the path. So immediately this will try to make the path restricted, and it will change this path. So there in localized there will be a turbulence flow. That will be a turbulence flow will occur in this area. But if we follow the path long, because if we consider this a very long distance, the immediate one will be turbulence flow. But if we follow this part back, there could be a possibilities that at any cross section, earlier if there is no restriction, the what we can say, the velocities in any segments are same for any particle. If the particle following this path, if the velocity is there is, let's say, 2 meter per second, and if it is 4 meter per second, so that will flow accordingly. Now when certain restriction has come, so what will happen, this point there may be a deviation of velocity that may reduce to this much, but that may not be uniformly disturb this area, because this is very near a point, so this will be affected more. There may be something, if I say this will be disturbed by this much only, so there will be a reduction in velocity also. There will be a reduction in velocity, but the difference of the velocity for this distance is, earlier it is 2 meter per second. Now suddenly this has reduced to 1 meter per second. Okay. Okay. So, and this could vary, even if I consider this is of 1 meter length, this is the next 1 meter length, the reduction here may not be uniform. That way it will reduce. There may be a different value will come between the velocities. So this kind of flow, due to this restriction, somewhere in between from the steady flow and the long distance, there could be still a steady flow, but in between the effect for this restriction could be something which is non-uniform, not so steady. So that will come as a unsteady flow. Due to the sudden close of valves, the effect on behind it, immediately there will be a turbulence. The effect behind it would be non-uniform, that not being reduced uniformly with uniform distance. That could be a different value for each same distance considered. Okay, so this kind of flow will come considered as a unsteady flow. Okay, this is the overall understanding of a different kind of flow. And now we'll consider the mostly the first kind of flow, that is the steady steady or streamline or the laminar flow. We'll talk on this. Okay, fine. So our first phase of study, you can say, to be the steady or the streamline or the laminar flow. So every term of this having their own meaning, but all are representing the same kind of flow. So steady means as the you can correlate with the steady speed, steady motion. In steady motion, the change in velocity or the uniform velocity, whatever you consider, with the respect of time, is same. So that means if a vehicle moving with a constant speed, that will maintain the constant. If vehicle is moving with a constant acceleration, the change in speed for any time lag will act as a similar way. That means it almost a linear way. So that means if the change is in between these two span, if it is, let's say, x, the next x, the change this will be similar. That means I can say y by x or dy by dx. Basically, in smaller change, if I consider the instantaneous change, dy will come. Otherwise, for bigger change, because this kind of flow, fluid flow, is always an instantaneous thing we have to consider. As you have read in kinematics, the instantaneous velocities or the acceleration is considered where there is a tiny change of the dependent variable with respect to the independent variable, that means dy by dx is a constant. So I have meant to say, when dy by dx, the tiny change dy against small change dx, the independent variable, if it is constant, then we can say it is a steady state. So same as happening for steady state. Steady state means whatever is changed, what we are changing here, velocities. So the change in velocity with respect to time or with respect to the distance, you can say, will be same if I even consider any segment of the flow path. Okay, so the change will be same. So that is the steady state flow. Streamline streamline is the same replica of the thing that is explained in steady state. What is that? If a particle starting from, let's say, this is the terminal, and flowing, taking the same curvature of the tube of the or the contour on which it is flowing, because this is the boundary that is controlling the flow path. Now every particle will flow taking a path. Okay, and any particle is flowing following this particle, then because the liquid is full of particles, so each particle, if I consider, is following a path, and all those particles which are following this path is called the path of the particle in steady flow, or the path itself is called the streamline. So this is a streamline for the particles which are following this path. There could be different streamline which are followed by different particles. So each pathway is called the streamline for those several particles which are this particular path. So the line itself or the path itself is a called the streamline flow. Streamline. So the particle should flow in a streamline. So that will flow taking a path. These are called the streamline flow. Okay, but that is not happening for other case of flow, because this streamline flow maintains when there is no change in the flow parameters. So unless there is a flow parameter, that means any restriction and anything which is not governing to change its path, it will move in the same path continuously. So the streamline will be maintained till it is not being restricted by anything. Okay, so that's why steady flow in other terms can be said to be a streamline. So streamline can be maintained when there is a steady flow. You can say like that. Streamline only can be maintained when there is a steady flow. Okay, so this is the case. And the lamina is the flow. If I can consider the flow path to be a path of layer after layer flow, you can say these are the layers of flow. So each layer are sliding on each other and they are flowing. So from center, let's say if I go up or down, there could be a layer, means this cross section. When we are considering this cross section, these are being considered to be a layer instead of a line. That could be a layer, means if I consider this, then again this path, again this path. So this layer are sliding down on each other. Okay, so this can be another way of assuming the, instead of a line, each particle following line, so there could be a different particle are in same plane, in a curved plane. They are forming a layer, and similar kind of layer are with the same geometry are flowing on each other. So these are the one kind of laminar flow. Understand? So these all are related till this is a steady flow. So steady flow will be there, then streamline will be there, then laminar flow will be there, will be maintained. Otherwise everything will be disturbed. Okay, so for basic understanding I will end up here. In the next video I will move on more details on this steady, laminar, because this has to be defined. Apart from this understanding, that has to be defined to establish some relations between the flow parameters, so that we can establish mathematical relations to study it more practically. Because at the end, with this theory, if nothing mathematically is related, we cannot make our foundation to study, or you can say it has to be some foundation with some assumptions. Just like incompressibility is an assumption, there cannot be a practical one, but you need a base to study further. If any deviation, you can correct our basic relations and can study further. So these are the fundamental thing that has to be established with respect to their parameters, that has to be related ideally. Then after we can study with some deviations. So my basic intention to establish the fundamental relations among those parameters. So not only the theory, I have to bring some relations among those parameters. So that I will do in the next few classes. So here I am stopping, concluding this laminar flow. What you have understood by this, then that will be more clarified in the next classes. Okay, so as of now I'm stopping this episode here, and the next video I will come with more characteristics and relations. So thank you for now.